Sorry if I seemed dead in the last video. I definitely was, but it's important that we work on the interview questions because I want you guys to pass your interviews. So now we're going to talk about rotations and matrices, very related topics here. The first is that it's sort of an interesting paradigm, but rotations are always through a plane around an n-2 dimensional subspace. So I find that's actually a really useful way to think about rotations, and I got this from I think it was an Inner Product article by John Blow. But basically the idea here is that if you're doing a rotation in 2D, how would you think about that, right? One of the ways is to think about it using this concept, and in that case, it's always going to be around a point. A rotation in 3D is always going to be around a line. Similarly, if you were going to do a rotation in 4D, I guess it would always be around a plane. So I think that's an interesting way to sort of conceptualize that, and it makes sense when we go into matrices here because each of these matrices represent a rotation around a given axis. So this Rx represents the rotation matrice for a rotation of theta degrees around the x-axis. And you actually do, I think you should memorize what these matrices look like for a rotation around the X matrix, the Y, and the Z matrix, respectively. So I have gotten questions like, hey, describe to me a rotation matrix. And so that's one of the things you're going to want to do. Okay, so the other thing is to talk about quaternions. Pretty much the one thing they want to know about quaternions if you understand Gimbal Lock. Quaternions have 4 elements instead of 3, which would be a traditional Euler angle, an Euler rotation vector. And so there's actually a linear operation which you can do to get from one to the other, or an algebraic operation, and that's using the atan and the asine functions. The atan or arctan function is actually represented here. It's kind of curious, but it's actually equal to the angle that represents, in this sort of like unit circle setting, in order to get to the xy coordinate that's specified as the input. But it's reversed, so the input here is y comma x. So that's what arctan is, arctan2 is. And then just to understand Gimbal Lock, to achieve Gimbal Lock in an Euler system, simply align 2 axes of rotation by rotating any direction so that the 2 gimbals, these are the rings of rotation, are on top of each other. And that loses a degree of freedom, which you can of course regain, but the problem is that you can't regain it smoothly. So when you're linearly interpolating, it's not going to work smoothly on a quaternion. Or sorry, it's not going to work smoothly if you are in a Gimbal Lock situation. And so that's why we use quaternions instead. So with a quaternion, though, you can't use, well, you could use lerp, but it's more common for you to use slurp. However, slurp is more expensive, and so there's a good article, I think also in Inner Product, which argues for or against using slurp versus a normalized lerp. But you should just understand the trade-offs there, I guess. Okay, so let's talk more about matrices. The determinant of a matrix is the scalar of the volume or area represented by the transformation matrix, and if it's positive, that will mean that it maintains the orientation or handedness of the inputs. Orthonormal. So this is going to come up. Keep in mind, all rotation matrices are orthonormal. That's very important to remember. It's like an axiom to memorize. And if it's orthonormal, then this means that, for example, any column vector is going to be of length 1, and any column vector is always going to be orthogonal to all of the other column vectors. And the same applies for any row vector. It's length 1, and it's orthogonal to all other row vectors. That means that a set of the columns or rows form a basis. And additionally, if a matrix is orthonormal and square, that means that its transpose is also its inverse. So if you need to invert that matrix, I can't think of a purpose why you would need to do that right now, but if you need to do that, it's actually a lot simpler to just take the transpose rather than doing a more complicated method for finding the inverse. Okay, and then we spoke about this in a previous video, but a transform matrix, these come up a lot. So this is a 3x3 section, which represents rotation and scaling. Then this section is really just a 0 vector, it's empty space. Here is a 1, it's a placeholder. And then here is the translation. This is a 1 by 3. And then here's the determinant of a 2 by 2. And then here's the determinant of a 3 by 3. It's a much more complicated process. Okay, so that concludes a review of rotations and matrices. Join me next time for multi-threading. Good luck.